the idea of what we call a truncated power series. Okay, so we have this power series we saw in the analysis module. And now we are looking at the kinds of objectives and the kinds of repetitive questions that are asked in this module. And the question that is repetitive when it comes to Chev-by-Chev polynomials is the question of an economized series and the idea of what you call a truncated power series or terminated power series. For example, we ask the question, what is the purpose of economizing a power series? Okay, right. So we answer that question. Right. So we're going to look at that one there. So now, what is the purpose? So the purpose of economizing a power series is as follows. Right, is as follows. Obviously, when we economize, we reduce the order, but we note that if the order is reduced, we eliminate the higher order terms in the polynomial expression. So in other words, the idea of an economized power series gives the same accurate results as the original series, but the terms are fewer. So in other words, an economized, right, an economized. Right, so an economized, you can use the American Z, use the American Z for the economized, but yeah, it depends. The British normally use S, but the Americans use Z. Right, so doesn't matter. But yeah, it's popular to use Z in this module, so we maintain that. So in other words, an economized power series gives obviously we use the word almost because it's an estimate. Right. It gives almost the same accuracy. Gives almost the same accuracy as the original series. As the original series. With fewer terms. With fewer terms. If it's economized, then the terms are fewer. Okay, we saw that. We shall reinforce that right now. Okay, so obviously at the end of the day, we say the terms are fewer. So with fewer terms. Okay, with fewer terms. Right. With fewer terms. Right, so with fewer terms. Okay, we continue. With fewer terms. With fewer terms. Okay. There we go. Now the next question is economize the power series. So this is the kind of question you're going to meet this time around. Right. Economizing a given power series. Economize the power series that has been given. So now to economize the power series. So the power series is actually that one there. And so we move on to the next page. So it's A Roman figure 2. Right. So in A Roman figure 2, we look at the fact that the power series is given by, well, we saw it, but I'm just noting it because we're on a different page now. Right. So the power series is given by p of x, a polynomial function of x, which is actually 1 minus x plus x squared. That is the defining equation of the power series, minus x cubed over 3. Okay, our discussions are just intended to bring familiarity with the concepts. X to the fourth power over 4. Okay, this is given. This was just given like this in this question. And you're asked to economize it. Right, so the power series is given by so that the economized, right, the economized power series, right, so that the economized power series is as follows. So how do we economize it? We subtract, always like we did last time. Okay, so we take the power series we need to economize, so we need to reduce the power. Then we recall what the other polynomial is, okay, on the previous page. And now you recall that the other one, t sub 5 of x is 16x to the fifth power, etc., minus 20x cubed plus 5x. And we write it down here. So we economize the power series given by that, but also we write t sub 5 of x, which is the same as t sub 5 of x, which is the same as 16. 16x to the fifth power minus 20x to the third power plus 5x. Right, so the economized one, we did it last time, we practiced. So we will subtract the T5, we subtract this one here, the T5, which we call the share by share. Right, the share by share polynomial, so we subtract. Now, at this point, when we economize, we perform subtraction. Okay, we need to put a number here. We need to put a number there. The question is, what number do we put there?
Oh,
Yes, please.
how did you get this formula?
Okay, it was given in the question. Sorry.
Okay.
Yeah, they gave. Okay, here is the previous page. Sorry. Now, good question, but it was given because if you look very carefully here, you're given the polynomial, the truncated power series p of x, but also you're always given a power series, but you're also given a shape by shape polynomial. Okay, so it's so those two were given, and they'll always give. All right, we're just learning how to deal with this. So the next small little trick is to look at what happens here. So we need to subtract the T5, T sub 5. So we are subtracting a fifth order chef by chef polynomial, right? So subtracting a fifth order chef by chef polynomial, we put in a block a numerical value, and we multiply by T5 of x. Okay. The question is, what number do we put there? So first things first, we need to look at the highest power of the polynomial. We need to put the highest power. We need to consider the highest power of the polynomial. So we have here, for example, that we have minus 1 over 5 is the highest power of the x term. But now the question then is, what is the highest power in the other chef by chef polynomial? Well, the coefficient of the highest power is 16. So what do we multiply these by? Okay, so you need to work that out. So you need to remove this 16. How do you remove the 16? So to remove the 16 here, it means that you're going to divide by 16. So how do you divide by 16? So you put 1 over 16. But it's not enough to divide by 16 because you want it to be the same as the minus 1 over 5. So you will multiply therefore by 1/5, like that. Okay. But now what do we do? Do we subtract or do we add these here? Do we subtract or do we add these here? So essentially, for purpose of eliminating this, algebraically, we need to add. Okay, we would subtract if they were the same, because now we can see that if we subtract the x to the power 5, this is just algebraic elimination. So the x to the power 5 is not going to go away. But for it to go away, we must add. So which means that we shall have 1 minus x plus x squared plus x squared over 2 minus x cubed over 3 plus x to the 4th power over 4 minus x to the 5th power over 5 plus. So you have 1 over 16 by 5. Right, so you put T5, which is 16x to the 5th power minus 20x cubed plus 5x. Okay, that's what we have. So which is 1 minus x plus x squared over 2 minus x cubed over 3 plus x to the 4th power over 4 minus x to the 5th power over 5. And then now we're going to multiply by 1 over 16 by 5. Why 1 over 16 by 5? We want to remove this 16 in front of the x to the power 5 of the t sub 5. Simultaneously, we want to multiply x to the 5th power by 1/5. So you can write 16, then you have 16 by 5. You have x to the 5th power minus 20 divided by 16 by 5, x cubed plus 5 divided by 16 by 5, x, okay. Let's simplify 1 minus x plus x squared over 2 minus x cubed over 3 plus x to the 4th power over 4 minus x to the 5th power over 5. Okay, 16 cancels, leaving us with 1/5 x to the 5th power. Here at this point, we simplify this. So if you simplify this, you can divide, let's see. Okay, 5 goes how many times into 20? It goes 4 times. But now 4 goes how many times into 16? It goes 4 times. So this is the same as x cubed out of 4. Right, plus the 5 divides and we have 1 over 16x. So what is the result of this? So we continue. So now we have this one cancels here. And then what do we get at the end of the day? So we have this one here. And we have this one here. Okay, let's start with the constants. So 1 is the only constant term here. Okay, let's look at the linear terms. There's minus x. Another linear term is at the end, which is 1 over 16x. Right, so at the end of the day, which is minus 15 over 16x. So we are done with those terms. Okay, let's check. So we're just doing algebraic manipulation. So we need to make sure that we're just doing yeah, that's fine. Okay, now let's look at the quadratic terms. Right, so there's only one quadratic term. The only quadratic term is x squared or out of 2. So this is therefore the same as x squared out of 2. Okay, so we're done with the x squared. So now we have the cubic terms, which is x cubed over 3 minus x cubed over that. So which means we're going to multiply by, we add these. What is minus 1/3 minus 1/4? Right, so minus 1/3 minus 1/4, you can multiply this one by the first one by 4 and the other for 1 by 3. And so you have 4, and 3. So that gives you 7. Okay, we're just adding that gives you minus 7. So it will algebraically give you minus 7, right? Minus 7. Minus 7 out of 12 x cubed. Okay, so we dealt with the cubic terms, and then we have the fourth order term, which is x to the fourth power over 4. So this is the answer. Okay, this is the result. So which means at this point we have p of x plus 1 over 16 times 5 p5 of x. P5 of x. Okay, so now what was the question? We had to economize the power series. And so we have managed to economize the power series. Hence, the power series has been economized. Hence, right, so hence, the power series, has been economized. Has been economized with Z. All right, we're done with that question, A, Roman figure 2. All right, next, we look at the next question. And the next question is Roman figure 3. What is the maximum value of t sub 5x in the interval that? What is the maximum value of the power series? Of the shape by shape polynomial? Okay, we're looking at Roman figure 3. And in Roman figure 3, we're asking the question, what is the maximum value of t sub 5 in the interval that? T sub 5 is that. Right, so, okay. Okay, this question expected in the exam this time around. So we're looking at A, Roman figure 3. All right, in A, Roman figure 3, we're asking the question, what is the maximum? What is the maximum value? What is the maximum value? Value of the modulus of t sub 5 of x in the interval minus 1, 1. Okay, and obviously we have a question there, question mark. And this becomes the result. Right, so I want to find the maximum value of the modulus of the shape by shape polynomial, and this is how we do that. So, but recall that t sub 5 is equal to. Recall that t sub 5 is equal to. It was given in the question. So t sub 5 is actually equal to 16 x to the 5th power minus 20x cubed plus 5x. Okay, it was given like this shape by shape polynomial. So how do you find the maximum value of the shape by shape polynomial is part of what you need to learn in this course. And therefore, the maximum value is the modulus of this. The modulus, but also we are finding the maximum of it. So we put max. So we have this. We have this. So now, what do we get out of this? Right, what do we get out of these? So the maximum value then can be obtained by getting the maximum between 1 and 1 3 sub 5. 16x to the 5th power. X cubed. So now we have x and y. So if you substitute any of these values here, you substitute 1, because this is a compact interval called compact. Compact in mathematics means it is closed. It is closed and bounded. It is a closed and bounded interval, and therefore is called compact. So at the end of the day, then you have what? 16 to the 5th power minus 20 to the 3rd power. 1 modulus. Right, so this one is exactly 21 minus 20. 21 minus 20. And therefore 21 minus 20 is what? Right, it's 21 minus 20 is 1. It is exactly what? 1. So the maximum value is 1. Okay, I mean, a couple of things you can look at. What about if another student, because you need to substitute the values of x in the interval until you get the largest one. But you understand that the maximum is obtained at the extremes mostly of the interval. So you can have, for instance, 16 minus, in other words, at x equal to minus 1, you'd have 16 that, you have minus 20 minus 1 cubed plus 5 into minus 1. This is minus 16 plus 20 minus 5. So this is minus 21 plus 20. But we have the modulus guaranteeing the positivity of the result. So we have that this one is exactly minus 1. So that the result is 1. The result is 1. So the result is 1. Okay, so in the end, then we see the result is 1. Okay. There are a couple of ways to reason this out, but there cannot be a value that is bigger than 1. Okay, right. So because you can see it is the case at x equal to minus 1 and also at x equals 1. So what is the maximum value of the Chebyshev polynomial in the closed and bounded interval? It is 1. That is the maximum value. The next question is we need to be able to answer questions like this for exam purposes. Questions like this. Right. If Q of X denotes an economized series obtained in Roman figure 2. Okay, so Q of X is the economized, denotes the economized series. So we're going to take that the economized series in Roman figure 2, and we shall call it Q of X. And then asking the question, what is the maximum value of the difference? Q of X minus Q of X in the interval.
Hello?
Yes, please.
What is economized?
Economized. Okay, that's a good question. The economized series is because of the first Roman figure. Right, we said what is, right, okay, here is Roman figure 2. We're asking the question, economize the power series. What do we do when we economize the power series? What do we do? We actually eliminate the highest degree. So if we economize, we actually eliminate or remove the highest degree from the power series. right, the highest degree term. Right, so we remove the highest degree term from the power series. Okay, so we remove the highest degree term. So if we economize the power series given, what do? We eliminate this one. We eliminate this one. We take it away. So that's what we do. But now for us to take it away, we must have a Chef-by-Chef polynomial that contains the highest degree, this the sort of term that is the same higher degree or the same highest degree. Okay, because the highest degree is 5. So we economize. What does economize mean? Is to eliminate, because it's algebraic elimination. So we perform algebraic elimination like in simultaneous equations. We remove the highest degree. So in the fourth Roman figure, we are saying what is the maximum value of the difference? Right. Q of x now denotes the economized power series. So we take the economized power series from Roman figure 2. Okay, we're going to call it Q. And then now we then obtain the difference between P and Q, the economized power series in the interval that, and we're asking the maximum value of the difference. Okay, we look at that question. So that is Roman figure 4. Right, so in view of Roman figure 4, in view of Roman figure 4, we proceed as follows. Right. Right, so we're going to say Q of x is P of x minus 1 over 5 by 16. So which is Q of x minus 1 over 80 P sub 5, from which we obtain, okay, we did this before, so we're just calling it Q of x. We explained why we are multiplying by, we are actually adding. We explained why we are actually adding here. We added. Now we add or we subtract. So we added because addition was the most appropriate binary operation that would eliminate the highest order term. Okay, so now then the conclusion then is that then we obtain the absolute value of the difference, P minus Q, because they want to find the maximum value of this. So, okay. So we look at what happened here. So this is just algebra. So if you look very carefully, okay, I'm going to write something here. So if you look very carefully, then we have these, but this means that we can be able to obtain the P of x. P of x minus Q of x. What is P of x minus Q of x? P of x minus Q of x is minus 1 over 80 P sub 5 of x. So, and this modulus, so it's just algebra here. You manipulate this and you take this onto the other side of the equation, etc. So it becomes negative. But then we take the modulus of the red equation. Right, so now we'd have the modulus of minus 1 over 80. P sub 5 modulus. Okay, the modulus of this now is the modulus of the 1 over 80, which is positive. Then you have the modulus of T sub 5. So what is the answer? So the answer is that therefore this is T less or equal to. Less or equal to. We saw that the maximum value of the T sub 5 is 1, so that this is 1. And therefore this is 1 over 80. Obviously, upon further division, we're able to see that this difference here is 0, this quotient, 0.0125. This is true when minus 1 is less or equal to x in that. Or you could say, obviously, when x is an element of the closed and bounded interval, compact interval, this one. What have we got? What have we got? What is this that we've just obtained? We just achieved? Well, it's because we said, what is the maximum value of that? So in other words, you can come here and say, hence, the maximum value of the difference minus qx. This maximum value is what? This maximum value is exactly that. So you can write it 0.0125, or you can say the maximum value is exactly 1 out of 80. Okay. The next question. In view of the economized power series that we were given a power series which we just economized. And economization has to do with just the elimination of the highest order term from the expression. We want to find now, okay, we want to find a Pade approximation, R sub 6 of x, with the denominator of degree 3 to the function this. Want to find a Pade approximation R6 of x with the denominator of degree 3 to the function this. Okay. Now let's answer this question. So the first question is, in B Roman figure 1, why is it often preferred? Why is it often preferred to approximate a function by a rational function? To approximate a function by a rational function rather than by a polynomial. Why is it the case? Right, so we look at B Roman figure 1. B Roman figure 1. So we say here a rational approximation. A rational approximation can give greater accuracy for the same number with the same number of coefficients. Same number of coefficients or the same accuracy with fewer coefficients. Fewer coefficients. With fewer coefficients. Why do we prefer a rational function for purpose of approximation and a polynomial? Well, the reason is because the rational, right, the rational approximation can give greater accuracy for the same number of coefficients or the same accuracy with fewer coefficients. So in other words, rational approximations give greater accuracy relative to polynomial approximations. And that is why the rational approximations are preferred. So if you look at this question here, in B Roman figure 2, you need to be able to write down, for purpose of exam preparation, you must be able to write down R sub 6 of x with coefficients AI and BI. Write down R sub 6 of x with coefficients AI and what? And BI. We need to write down the rational function of degree 6. We defined this last time, but we just do it now again. Okay, we gave the definition, looked at an example, but we look at another one now. So this is what happens then. So we note that R6 of x is actually A naught plus A1x plus A2x squared plus A3x cubed. And this is divided by 1 plus B1x plus B2 or B sub 2 x squared plus B sub 3 x cubed. Okay, so we need to just write down R sub 6 with coefficients AI and BI. Just write the formula for R sub 6. This is the formula. How is this R sub 6? Okay, we discussed the fact that we want always to have the denominator must not be 0. In an attempt to ensure that the denominator is not 0, we ensure that we do a couple of things, but we ensure that the one that appears here in the denominator, ensure that even if the rest of the coefficients in the denominator, if ever these are 0, we do not have division by 0. And that's why the 1 is there. So this, therefore, we are just had to write down the formula R sub 6, and therefore you realize that it is the rational function of degree. Degree what? 6. Rational function of degree 6. Rational function of degree 6. set up the equations to find the coefficients, but do not solve the system. Okay, so we proceed now to set up the equations. The equations to find the coefficients. Okay, remember when we are doing the Pade approximation, last time we did that, we must be able to find the coefficients. But now what we're gonna do is we're gonna set up the equations, but they said, please do not solve the system. Okay, so that's interesting. So we're gonna just do that right now. And to do that, we proceed as follows. Would remember that at this point, we're actually dealing with the P Roman figure 3. And in P Roman figure 3, we are given the following. Right, so in P Roman figure 3, first and foremost, we are given the P, the e to the power x squared. We're given the e to the power x squared, which is 1 plus x squared plus x to the fourth power over 2 plus that. So which is e to the power x squared. Which is 1 plus x squared plus x to the fourth power over 2 plus x to the sixth power over 6 plus. So we have. Okay. We have this. And then we want to find the Pade approximation. Now look at the objective of this question B. We want to find the Pade approximation R sub 6 of x with denominator 3. We put a denominator of degree 3, okay, to the function that. So remember that to find the Pade approximation to a function, we actually proceed as follows. So this is something you really can expect to meet. So we x squared, I'm putting the cube there. So you have x squared here. So we subtract. We subtract the rational function of with a denominator of degree 3. And now when we do that, we proceed as follows. So we're going to have ex squared, then we subtract R6 of x. Right, and if we do that, we proceed as follows. So the e to the power x squared is this power series. Is the power series of this one here. It was given. But now we subtract R sub 6. To find a Pade approximation, the Pade approximation here is R sub 6 of x. And now, what is it the same as, this Pade approximation? It is actually the same as, we just saw that. Okay, so the Pade approximation with a denominator of degree 3 denominator of degree 3, means that here a1x, a2x squared, a3x cubed, 1 plus b1x, b2x squared, b3x cubed, so we get these. Okay. After this, we can take the lowest common denominator, the LCD, of the two fractions. X to the 4th power over 2 1 plus b1x plus b2x squared. And then you subtract a0 plus a1x plus a2x squared plus a3x cubed. Okay, we just took the LCD. We divide by b1 x plus b2 x squared plus b3 x cubed. Okay. Now we have this. Now we have this. But we make certain observations that in the numerator, set the coefficients. Set the coefficients of terms one x up to up to x to the 6th power equal to 0. In the numerator, set the coefficients of terms 1x up to x to the 6th power equal to 0. You note that this is what we did last time. So we want to find the Pade approximation.
Hello?
So yes, please.
Where did you get this from?
Okay, that's a good question. Where did I get that from? It's R sub 6. It's the polynomial we use of degree 6. So it came from here. It's the blue one at the bottom of the screen because they said here, write down R sub 6 with coefficients a, I, b, I. So I wrote R sub 6 of degree 6. Okay. So R sub 6 of degree 6 is actually this polynomial that has degree 3 in the numerator and degree 3 in the denominator. But in other words, you just divide two polynomials of degree 3, but you just put a 1 here. That is the formula always, okay? And so it's always this way. So, I mean, it is always of even order, because now, for instance, if they can say write R2, maybe R4, because R3 is a bit too small. What is the formula for R4 be? Okay, we did one last time. Just need to remember what degree it was. Okay, R sub 4 would mean that the denominator, right, the denominator, right, the denominator has degree 2. So the degree is always half of the denominator. So let's half that number. So why is it half that number? Well, it's half that number because then you have 1. So it's of degree 2. It's a quadratic. The quadratic we know is ax squared plus bx plus c. But now we just make c 1. If c is 1, then we just have only bx plus ax squared. Then what do we do with the rest of these? At the top, you can put anything. So you can put literally anything. So you can put p plus qx plus rx squared. Okay, so this will be R4. But here they said they want what? R6. Okay, now obviously R sub 6, now they said you need to find the Pade approximation with a denominator, of degree 3. That's why it's R6 of degree 3. Okay, so that's where it comes from. Now, in the numerator, you set the coefficients of terms 1, x up to x to the power 6 equal to 0. Equal to 0. Right, so when that happens, okay, we need to multiply these, but I know that it's going to be a long thing. But okay, hence this it just says is thus for purpose of practice. Consider the numerator. So the numerator is going to be 1 plus x squared plus x to the 4th power over 2 plus a2x squared plus a3x cubed. Okay, so you multiply through now here. When you do, you have 1 by 1. Okay, this is going to be emission. 1 by 1 is 1. And then first, let's multiply by 1, multiplying these 3 by 1. So it's going to be the same thing. And then now you multiply by x squared. Okay, then you multiply by x to the 4th power. Okay, so it's this. Okay, and then now you continue to multiply by x to the 6th power. And then you multiply it by x to the sixth power. And then you multiply it by x to the sixth power. Okay, so you put 9 here. Minus a naught minus a1x plus a2 x squared plus a3. Okay, right now what you need to do, you just deal with the constants and the rest of the terms. Okay, so we just will consider the terms and then we group like terms. Constants is 1 and a naught, so we're done with this one, we're done with that one. Okay, those are constants. And then we look at the linear terms now, which is b1 minus a1 minus a1, and then you put x. So you have that. Okay, now you look at the quadratics. Okay, we have that quadratic and then plus 1. Quadratic that. And then you have this one. Okay, this is minus, please. This is minus, and this is minus. So you have minus and minus. So you have b2 minus, okay, just a sec. Right, so you have the x squared, which is b2. And then we have minus a2. Okay, so you have x cubed. Right, so now in view of the cubics, you have b3 plus b1 okay, plus b1, okay, and then you have the b1 there. And then you have another cube minus a3. Okay, just one sec. Right, so we continue. Now the x to the fourth power would have b2, this one, x to the fourth power plus 1/2. And then you have x to the 5th power. B3, x to the 5th power. That's half. Okay. And then we have x to the 6th power. And then there's x to the 6th power. 1/6, this one. Okay. Now, the observation we are making here is that hence, which is x, the constants is a minus a naught. The one for x is b1 minus a1. Is b1 minus a1. And then x squared, b2 plus a1 minus a2. b2 plus a1, no, let's check. b2 plus 1 minus a2. b2 plus 1 minus a2. Let's look at x cubed. X cubed is b3 plus b1 minus a3. b3 plus b1. b3 plus b1 minus a3. b3 plus b1 minus a3 equals 0. X to the 4th power. The coefficient of x to the 4th power is b2 plus 1/2. b2 plus, we equate them to 0. Always we do this. Always we do this when it comes to the Pade approximation. So we have x to the 5th power. Is b3 plus half b1. b3 plus 1/2 b1 equals 0. X to the 6th power. 1/2 b2 plus 1/6. 1/2 b2 plus 1/6. One half b2 plus 1/6. Okay, these equations need not be solved, but I'm going to say it is possible right? Solving the equations, solving these equations, yields the numerical values of A naught, A1. Okay, we need to obviously obtain those. And then we find all of them, because now with the R6, okay, we wrote the R6, R sub 6 of X for the Pade approximation. So now this one, one plus B1X plus B2X squared plus B3 and then we have A naught plus A1 plus A2 plus A3. So we need to find all the values of these things. If we can say we have found the Pade approximation. So we'd find A naught, and then we find A1, and then we'd have to find A2 in the numerator, and then we have to find A3 that appears in the numerator. And then obviously we obtain everything, the B1 also, but also we obtain the B2, we also obtain the B3. Okay, well, we can solve this simultaneously. But they said in this question, do not solve. Hence, the Pade approximation is determined is shown above. Okay. Why did we stop at x to the power 6 here? Why did we stop? It's because we're dealing with R6. We're dealing with R6 because if you check very carefully, now when you get into these, there are higher powers here. There is x to the power 8, there's x to the power 9, this one, there's x to the power 8, there's x to the power 7. All these things are appearing here. 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 Okay, the x to the power 6, yeah. But we stop at x to the power 6 because it's using R6 and we equate the numerator to 0, etc., etc. As we said here, in the numerator, set the coefficients of terms 1x, x squared up to x to the power 6 equal to 0. You need to set the coefficients. You set the coefficients equal to 0 and then be able to solve this simultaneously, and that will give you the Pade approximation there. Okay. So we have answered this question. We continue. Okay, now this is something that we looked at last time. Okay, but obviously there can just be small differences and you need to just reinforce. But it's a very popular concept that will always feature in the exam, pretty much 99.9% of the times. In my collection of popular questions in this module, and as we attempt to cover this, we're here to cover more methods. it really appeared important to sort of reinforce this idea, but I know it's not a difficult one at all. Okay, whether this is similar to that, it can be different. Okay, but it appeared very popular in collections of questions. In collections of questions. So what do we do now? Okay, using 3 digits. Use 3 decimal digits with rounding at each step. We just give the estimates of those two. So in other words, the predictor and the corrector formulas of the Adams-Moulton method are given by this. We already know the two formulas, right? But now to apply them to a concept, to a situation is something that must be mastered because it's going to be in the exam. 99.999%. Now, given this differential equation and the starting values of t, now the starting values of t start from 0 and then 0 0.2, 0 0.4 that, and therefore that means h is the step which is 0 0.2. Okay, so you have 0 0.0, 0 0.2, then 0 0.4, 0 0.6. Okay. Right, so y primed. Y primed is actually t plus y. But we remember that y primed for us is actually a function of the two variables t and y. The given starting values are given by the given starting values. Starting values are given by. So we draw this table. We draw this table. Right, so the given starting values are given by. Right, so we start with n equals 1, n equals 2, n equals 3, n equals 4. Okay. Now we have here something. Gonna put this here. We're just practicing this method. It's very popular already, but we're reinforcing our understanding of this. So we would have T1 T1 is the first one, 0.0. Then at n equals 2, we have T2. N equals 2, we have T2 equals 0.2. And then we have T3, which is 0.4. And then we have T4, which is 0.6, excuse me. Okay, there's some things you need to note. We note the fact that this is in steps of 0.2 because our age is, so it's 0.2, 0.4, 0.6. So at 0.2, then we have n equals 2. At 0.4, we have n equals 3 and so on. Okay, this is going to be in the exam pretty much. Now, there's something we need to as well remember. We're given this. We're given those values that of y at n equals 1, there's 0.95. N equals 2, 0.68. N equals 3, 0.55. And n equals 1, 2, 3, 4 is 0.3. So we write those ones down in the table. So they've been given. So this one, 0.95, y2. It's already with this module, it's very important to just understand the popular methods that are examinable as we are on a journey to exhaust the rest of the examinable concepts. Okay, the methods that must be known for exam. We know that y4 is 0.30. Then there's f1, f2, f3, f4. Okay. So now, the question therefore is, what are these ones? Okay, you can easily get the F's. Okay, because the F's, the F of Ty is the sum of the T and the sum of the T and the Y. So this one is going to be the sum. Okay, but obviously if it is 0.0 plus 0.95, then it's 0.95. 0.2 plus 0.68 is 0.88. Okay, and then we add all of them because the y primed, which is fty, is the sum. So you have 0.4 plus 0.55, which is 0.95. And then 0.6 plus 0.3, which is 0.90, two decimal places. So 0 just 0.9. The aim of this method here is to say, after we got all these things here, we proceed to just give the estimates there. The two values. So we start with a value, 0.8, and then we go 1.0. Okay, I know this is popular, but we're just reinforcing our understanding of this. The predictor is, right, we remember that the predictor is the top formula, so you have them in that order. Predictor first and then the corrector. Predictor and then the corrector. So we have them and then you write them down, but we leave out the last order terms. So which means you have yn plus 1, yn plus h over 24, fn minus 59, plus 37, Fn minus 2. Okay, so now what y value will this predictor give us? Okay, with n equals 4, so now it's going to be at n equals 5. Because here we were at n equals 4. So at n equals, yeah, it will be at n equals 5. But now, okay, so we're dealing with n equals 5, and then that must be y5. We're getting y5. Okay, obviously n is at n equals 5. Then if you're getting y5, it means this one is 1 less. Plus 8 and 24. This one is 1 less. 4. This one is going to be 3. This one is going to be 2. This one is going to be 1. Okay, what is y4? 0.30. H is 0.2. 24. Fif- 55. F4. 0.90 or 0.9 minus 59. F3, 0.95. Okay, plus 37. This is popular, just going through it. F2, 0.88 minus 9. F1, 0.95. Which is 0.4455. Okay. That's what we get from this.
Hello.
Yes, please.
Is this question for Math 2613?
No. This is APM. It's 3711.
Okay.
Yeah. Okay. Yeah. Yeah. This kind of
And
discussion. Yeah.
the power series we were discussing,
Please come again.
the power series we were discussing power series just
Yes, we're
now.
discussing power series now, but now the things we're discussing today are 3711.
Okay.
Yeah. Okay. Yeah, there are 3711 things. I decided that we discussed that one because we discussed power series, but yeah, it's 3711. I'm sorry I did not mention because I thought maybe it was going to be obvious, but yeah, it's 3711 we're discussing now because obviously we're supposed to discuss it today. It is today's one at 1, but we just moved. You see, initially we had said Thursday would be reserved for this module. So simultaneously, then obviously, I mean, I understand the power series are popular, but we approach them differently and we use them for different purposes. Here, obviously, we speak of the economization and other things. Okay, so just note that. Okay, this is very popular, I know, but I said this is numerical analysis. Right. I'm just reinforcing some of the things here. I was saying hence, for instance, if we know that y primed is t plus y, which is f t y, so this one is going to become what? This one is going to become the same thing. So we are dealing with y5. So which means with f5, which is p5 plus y5, and call it 5. Okay, just putting the subscripts there. Okay, obviously at this point, if we know y5 and t5, t5 is this one because we're having t4 there. So it's 0.8, but the y5 is what we just got now, which is 0.4455 is f5. It becomes essential for us to find the f5 in our table. So it becomes the sum of this. Right, if you add 0.8 plus 0.445 is 1.2455. So f5, 1.2455. Hey, I said it's 26 is 3711. We're discussing now. Okay, we found the predictor and then we find the corrector. Right, so find the corrector. We're just practicing. Nothing strange, and then we go to something else. Right, so um the corrector now is given by okay, okay, we remember the formula for the corrector is always given, but yeah, I can just practice it. They will always give it in the exam because there's no formula sheet in this module. So the corrector is given by y sub n plus 1, which is yn, which is h over 24 into 9fn minus 1 plus 19 fn minus 5 n minus 1 plus n minus 2. And then we remember that we have those, but we truncate. We remove the 720. We remove the 720 here. H5, Y5. XI2. So now you'd have here the corrector Y5, which would be Y4, just one less, H24, Y1 less, 3. Um, 1 less, 2. No, 4. Okay, you just um, have to just obviously just maintain the accuracy. Right, so we have 19 F4 minus 5 F3, F2. So We continue. Um, so you'd remember that the Y4 is in the table 0.30. You're going to come here and put it here 0.3, 0.3, 0.30. The H is 0.2. F3, so from the table, 0.95. F4, 0.90. F4 is scale 0.90. Minus 5. F3 is the last column, 0.95. F3, 0.95. F2, 0.88. Okay, so we have this. Zero point 0.50, 0.5037. And then similarly, for the corrector, we get a different value of F5. Similarly, for the corrector, we remember that y primed is t plus y for this question, but it is f ty. So which means that we can put 5 here. T5 y5 equals f5 ty. So what is t5? 0.8. Because here we went up to T4, which was 0.6. T4 was 0.6. So T5 is 0.8, the next one after 0.6. So is a 0.8 plus the Y5. Right, obviously the Y5 we've got here. So which means that you add these things here. Right, so if you add these things, you get the corresponding F5 for the corrector. And the sum of this is 1.30 37. And this is F5, and that is that. Okay, this repeats. It repeats. Okay, that was for 0.8, and then for t equals 1.0. This is 0.8. So now if you say 0.8, you add 0.2, that is 1.0. It's 0.8 plus 0.2. We just keep adding 0.2 to get the successive ones. And then we get 1.0. And then we're going to do something for the predictor now, and then the corrector, and then we're done. Right. Now we shall close here because it's not really a problem. For the predictor, the formula for the Adams-Moulton is yn plus 1. I want to write that one first. Yn plus 1, which is yn plus h out of 24 55 n Fn minus here minus 59 Fn minus 1 plus 37 minus 9 Fn minus 3. So we're gonna obviously now do the same thing, but we're gonna do this is y6 now, because this is the 6. So T6 corresponds to Y6. This is one less, which is 5. H on 24. 5 F5 minus 5 F. 1 less, 4. 3 7. 2 less, 3. 3 less, 2. Yes. So this, we've already got Y5. Y5 was obtained before. What was Y5? Okay, we got Y5 for the predictor and we got Y5 for the corrector. So yeah. So the Y5 we got for the corrector was 1.30. No. The Y5 was 0.5. Is this one? Because I'm going to just be reading these values and like, where are these values? Okay, the Y5 is this one. Okay, we take it and we plug it into this, which is 0.5037. We take it from the corrector of the previous p-value. So which means 5037 24. What is F5? We got F5 for the F5 is this one. 1.3037. 1.3037. F4 is 0.9. F3 is 0.95. F2, we got it from the table. F2 is this one, 0.88. Then we use a calculator to do this one. Right, just recapping on these. Not take us, obviously, it's not going to take us a lot of time. But now this one, therefore, is 0.8856. Adams-Moulton. And now it is true together with the fact that y primed is t plus y for this question, but y primed is a function of two variables. It's a multivariable function. Now, being a multivariable function, y6, what is y6? T6, we've already got T6, 1.0. Y6, you add this, which is 1.8856. Hey. So now this is what we did, but now the things we did here were for the predictor, and then now we just go to the corrector in just a split second, somebody would say. Right, so in a split second. So now the corrector. But the corrector at T6, which is 1.0. Which is Y6. Okay, but before I do Y6, let me just do the general formula for the Adams-Moulton corrector formula. You remember that the Adams-Moulton corrector formula is given in the question, but it is given by this. Which is H out of 24. 9F n plus 1. Plus 19. Minus 5. Plus Fn minus 2. So you have 6 here for the corrector. And then this is 1 less, 5. 24 here. So this one is going to be F what? It's going to be F6 plus 19. This one is going to be 1 less than the previous, so it's going to be 5. This one is going to be 1 less, 4. This one is going to be 2 less, 3. Okay, so we continue and we do this. Okay, let's see now. What is Y5? Okay, so the Y5 obviously was obtained before. And Y5 was obtained from where? Right, so our Y5 was obtained from the, we got it here as well. Y5, got it here. And it came from the corrector of the previous calculation. It is from the corrector at t equals 0.8. So you have Y5. So which is 0.5037, 0.2, F6. We got F6, that one, which is 1.8856. And then we have 19F5. What is it? Okay, we got F5 again. What did you get F5 to be? Got F5 from the previous calculation. 1.30. This is F5, 1.3037. 1.3037 minus 5 into F4. What is F4? Okay, F4 is from the table 0.90, just 0.9. 0.90. F3, 0.95. So, which is 0.822. Okay, so we have this correct. So now we found the result. We found the result. So at this point, what we're effectively then saying is we had to get the actual estimates, apply the Adams-Moulton. So here an S is missing. All right, method to approximate this. So we found this, and then we go to 0.8, and then we go to 1.0. And then here, obviously, this one was N1, N2, N3, N4, N5, N6. Right, and then we get the rest of these. Right, so we got the estimates that are required for the predictor and the corrector. All right, and so after we got them, we have solved this question. 1.0 and 1.8. 0.8, excuse me, 0.8 and 1.0. That's what I want to say. The next question is question 4, which focuses on the idea of the boundary value problem. Okay, I'm just going to hint these because we don't have a lot of time left. And this question is going to take us, about 30 minutes to do. Let's see now. It can take us about 30 minutes to discuss. Okay, let's just pass through it. All right, let's look at this question 4. Right, we're considering the boundary value problem given by this second order differential equation, d squared y dx squared plus 2xy equals 2, x lies between 0 and 2. Set up the set of equations to solve this problem by the method of finite differences. So we're going to just be discussing the method of finite differences when h is actually equal to delta x. So we say h equals delta x, which is 1/2, which is 0.5, is used in each of the following cases of boundary conditions. You do not have to solve the equations. So we're not going to solve the equations for this case. So we just, it's going to be a bit shorter. But there are two specific values. If we're going to do part A, right, y at 0 is 5 and y at 2 equals 10. Right, and now we actually discussed this method of finite differences before. Right, and so we remember something. Right. The central difference formula. The central difference formula. Central difference formula. Okay. Right. So we need to set up equations to solve this problem. Now, we to set up the equations, we're gonna we actually gonna let xi denote the grid points. Okay. You remember this when did the ADI and the SOR and it comes up. So denote the grid points. Xi plus 1 and let yi denote the approximate value. Of xi. We'll use the following approximations. Right, we'll use the approximations that the second partial derivative of y with respect to x squared. So this is a second partial derivative. Evaluated at x equals xi, this is approximately this. Right, is approximately this. Right, this is a formula using this central difference formula. And therefore it is yi plus 1 minus 2yi plus yi minus 1. You divide everything by, this is a central difference formula, divided by x squared. So this must be known. So, which means yi. And of course, we watch the formulas. And of course, we note that at this point, we have that x itself x evaluated if x equals xi, which is the same as xi. Okay, we use this formula because we're dealing with d squared y dx squared plus 2xy equals 2 when x lies between 0 and 2. But also, I want to mention something here. The differential equation can be approximated at grid points xi by the difference equation. So the difference equation, right? So the difference equation the difference equation okay, the difference equation, this one. Okay, it's called difference equation yi plus 1 minus 2yi plus yi minus 1. We divide everything by h squared, 2xiyi. Okay, observe that the difference equation, that one, um, okay, because this one here is the second order differential equation of this boundary value problem, which equals 2. And therefore, this here equals 2. So what have we done? So in other words, we just converted the d squared y dx squared plus 2xy equals 2. We've written this now in this format. Hence, hence, the differential equation mhm, can be approximated. Can be approximated at a grid point. Can be approximated at a grid point Okay, so the method of finite differences is examinable, and we're just discussing it right now, and we're yet to go into detail of the Runge-Kutta and other related methods that we have not quite discussed as yet. The differential equation can be used, can be approximated, so we can take that differential equation that was given in the question. This can be approximated at a grid point by the difference equation. So now we want to solve the differential equation, but instead of solving the differential equation, we convert it to what we call a difference equation, which now is having these subscripts, y subscript I plus 1, and we have this. Okay, the observation, therefore, is that at this point, The observation is therefore that at this point, when H we remember in the question that when H is delta X, which is 1/2, would have in the place of H here, you put 1/2. You put 1/2. So if you put 1/2, it's going to become what? You write a step like this, obvious, but yeah. 2yi plus I minus 1. You divide by this. So now at this point, you can, so the half squared in the denominator is going to produce a 4. It's going to produce a 4. From which you're able to get 4. Yi plus 1 minus 8. Yi plus 4. Okay, and then you have 8. Xi equals, no, it's not 8 here. It equals 2. Okay, we're just trying to manipulate these, so we're making H 2 because it was given that way. But this one here is going to remain 2 because this 1/2 only divides the first 3 terms of the differential equation, of the difference equation. So this one remains 2. Okay, obviously we agree that at this point, this one here is can be divided through by 2, which is 2yi plus 1 minus, you divide by 2, which is 4 here. Yi divide by 2, divide by 2, which is xi yi equals 1. And then now we have this. What do we obtain from this? So we have yi is a common factor. So yi is a common factor. So you have 2yi minus 1. So we're done with this one. Then now we're going to deal with this. So if you factor out xi minus 4 yi. Okay. What you get? And then we have 2 yi plus 1, and this equals 1. All right. So this is what we have. Right. I'm going to continue in the next discussion. Because now it's just 8:38, but I'm going to discuss in detail the grid. 8:38.
When is our next lesson?
That's a good question. Our next lesson has to be tomorrow. Okay, I need to check the time for load shedding and whatnot.
Format
Tomorrow,
26.
yeah, for 2613 tomorrow. Let me see the load shedding. Because we still have a lot to discuss in 2613. Right, so let me see now. My load shedding schedule. I just want to check if I suggest the time for tomorrow. Let me see. I'm looking at my load shedding now. Schedule. Yeah, the load shedding schedule tomorrow. There's load shedding from 2 to 4, so we can only meet after 4. But just maybe we can make it 6 p.m. Think about it. Let me know. What time is suits
Okay.
you? 4. 4 is best for you, right?
Yes.
Okay, 4 is best for you. Okay, that's fine because if it's just at 4. Right, let's just, because my power is going to come back at 4 tomorrow, because they're going to be load shedding at 2, so we can't meet at 1 because it's going to be like 1 hour and then we experience the load shedding. So yeah, I'll see you tomorrow at 4 p.m. and we're going to be doing a lot of the 2613. And my plan is, so we might just alternate the modules. We shall see how to alternate them so that because the 2613 obviously is not very long. So, but you need to just, I'll bring more practice problems tomorrow on the different sections. I'm gonna get problems from the textbook in the study guide that you're also gonna use to reinforce the understanding of each concept so that we solve several problems on the Riemann integral, several problems on series themselves in terms of the alternating and whatnot, and yeah, obviously in terms of the absolute convergence, conditional convergence, and divergence, those kinds of things. Yeah, but I must thank you for joining us. I'll see you again tomorrow, just after 4 p.m. when my power comes back. So it can be like 4:15. Let's just say 4:15, because 4, sometimes the power delays a little bit to come back. Okay. All right. See you tomorrow. Thanks. Goodbye.